Hello, I'm Eric Martin, lecturer of mechanical engineering at the University of Maine, and this is our second video on SMath Studio, part 2 of 2. In our previous video, we looked at the environment, variables and units, math and result formatting, text formatting, Greek letters, subscripts and superscripts, and writing and editing equations. And you can go back to that video if you want to review it. But in this video, we're going to look at some more intermediate topics, such as angle measurements and trigonometric functions, the exponential and logs, vectors and matrices, differentiation and integration, user-defined units, and change of temperature, and we'll finish off with 2D plotting. So here we are back in SMath. First, we'll look at angles and trigonometric functions. Let's say we want to have an angle theta. Remember, we can make our Greek letters using our letters. So for theta, it's Q, and then Control G. We can also use our symbol boxes on the right, and that will give us our different symbols. And we're going to assign this to be, I can't remember if I said 60 or 90 degrees. Let's do 90 degrees. And I can insert my degrees two different ways. One is I can type degree and then type tab. And then now we can just hit enter, and there's theta. I'll show how to enter the degree symbol in just a moment. If we want to know what that was in radians, again press Q, Control G, and then equal. And then we can see that it's in radians. The default angular unit for SMath is in radians, as it is in most programming languages. And if we want to see if that's truly radians, we can just type RAD and then tab, and then it is 1.57 radians, or half of pi. If we want to know what it is in revolutions, we can select our unit and change the rad to rev, and then hit enter, and it's 0.25, so it's a quarter of a revolution, which is 90 degrees. Our trig functions are really simple. Let's look at the cosine of theta. So COS, open parentheses, and then I'll type Q for my theta, then Control G. I can type equal even though my cursor is right in here. I think I can type it anywhere, and that will give us 0. The cosine of 90 degrees is 0. We can do the sine of theta, but let's do something different. So I type sine, open parentheses. Let's do pi over 2. So P, Control G. I didn't hit Control G there, I hit something else, maybe Control F. Let's try Control G. Control G, there we go. Divided by 2, and that should give us 1, and it does. Notice how it changed pi to this bold. It recognizes it as a predefined constant. For our inverse trig functions, we just type an A before our sine, our cosine, or our tangent. So let's do the inverse tangent of 1, and what we'll do is we'll set this to phi. To make phi, it's F, Control G, and we'll assign it. So it's our shift semicolon, and we'll do A tan, open parentheses, 1. Now we can hit enter here, or I'm sorry, I can hit equal here, and it gives us our answer. If I don't want to see that value here, I can backspace a couple times until we get rid of that equal sign, and then I can show phi again, F, Control G. Now I'll hit equal. And here we can see it's 0.785 radians. If I want to have this in degrees, I can type DEG and tab, and that gives us degrees as we saw earlier. Or we can actually have the degree symbol. So I'm going to press the single quote, and that brings up a handful of units and functions. But right at the top, we can see the degree symbol. So I can double click it and it will enter, or if I single click it, it says press tab to insert. And we see the inverse tangent of 1 is indeed 45 degrees. Next, we'll look at the exponential, logs an imaginary number. Basically the exponential, or E. If we just type E and then hit equal, notice it again turns bold like it did with pi, and then we see it's 2.72. So we can always raise E to a power, raise it to the power of P. So we type P, Control G, and then there's that value, 23.1. For logs, just type log, and then we need to get tab, and that will give us our base. We can put a base 10 here, and then let's just put 4. Then we can equal that, 0.602. If you want to confirm that, 10 to the 0.602, and I just type 10 caret to raise it to the power of 0.602 equal, and we can see that it's 4. If we want to check the significant digits of that, we again can look into our decimal places. Let's give it 6. We have both of these 6. So it's not exactly 4, but it's also not exactly 0.602. As you can see that we can get more precision the more decimal places that we include. The imaginary number I, that's a square root of -1. And so we can use the backslash to get to the square root symbol, -1 equal. And what we have displayed here is the real root and the imaginary root. The imaginary root is the 1i. So if I even just type I equals, we can see that we have the same thing. We do I squared, and we get -1. We also have function buttons for the logs, the natural log. I didn't talk about the natural log. Oh, I didn't mean to press it there. Control Z will undo. So just by pressing the button, we can get our natural log, or we can type it out, ln, and then tab. We'll look at vectors and matrices next. To create a matrix, we can either press the Control M, and this will ask us to insert the number of rows and columns, and we can change this. Or we can press the icon up here in our toolbox where it says matrix, and again it asks us for the numbers of rows and columns. So I can enter values into my matrix. To go between the indices of the matrix, I need to press the left or the right arrow key. If I press up and down, it's going to pop out of the matrix. I'll press up. You can see it, how it does that. I press down to get back into it. If I press down again, I bet I'll go into 11, differentiation, integration, yes. So left and right is how to move between the indices, or you can just point and click. So 6, 5, 4, and so forth. So you can assign a matrix to a variable. So I have capital I, and I'll assign that. And then I'll press Control M. And let's just do a 2 by 2, and we'll make an identity matrix. I is equal to that identity matrix. So to create a vector, we need to create them as columns. So I can go ahead and create a matrix, but make a single column. And let's give this a value of 1. Use my arrow key to get -3, my arrow key to get 2. And what I want to do is I want to make this as my R vector, maybe a position vector. So I'm going to type R. And I'm going to set that to be equal to something, or assign it. And I'm going to come over here back to my original vector. I'm going to highlight it, Control X. I'm going to come to my empty spot here and Control V. And so that's a way that we can move our elements around, or our variables and values around. Let's make a unit vector, U, and we need to make that as a column vector. Let's try the shortcut, Control M. And let's give that a 0.707 arrow key, call it 0 in the J direction, 0.707 in the K direction, if you're familiar with unit vectors. If not, that's okay. And let's go R times U, and this is going to give us a dot product. So to create a dot product, it's just the asterisk above this shift, or above the 8. I'm going to expand my sheet. Let's give no bounds here. And let's make another column vector. We'll call this one F. It looks like if F has already been predefined, but we will redefine it, and we're able to do that. And Control M, 3 rows in 1 column. Let's give it some larger values for a force vector, for instance. Let's do a cross product of R cross F. This would yield a moment vector. For cross products, we have to have 3 by 1 vectors. R cross F. To get the cross operator, we must use a Control 8, not an X, but the Control 8, then F, and then equal. And there would be our moment. In fact, if I want to have, let's back this up a little bit, and let's make this, I don't think I can put the M in front of there. I'd like to put the M in front, but I'm not able to, so I'm going to have to do this again. I'm going to have M, assign that, that'd be a moment. And then I'm going to, I can't drag and drop. I'll have to Control X and then Control V. And then we can have our moment. So we can actually put units after our vectors. I'm going to give myself some more room. Let's put units on our vectors. So now that we already have a vector, we need to press the multiplication sign, or the asterisk. And let's give this inches. Need to press the tab. And for our force, let's give that, how about we put that in newtons? We'll change our units, we'll combine them. So it gave some wonky units here, but let's go ahead and make this, let's make it to be Newton meter. So I'm going to press single quote n times single quote, how about millimeters, mm. Force times distance. So if I want to call out, let's say, the third index of my m vector, I'm going to type m and I'm going to create an index. It looks like a subscript. Subscript we use the period, but I'm going to use the open bracket. And when I use the open bracket, it looks, again, just like a subscript, but I'm going to call this 3, and then I'm going to hit equal, and it converts it to joules. So let's make this into joules. So we see the 4.83 joules. That's the third index. Second index is the 2.79. If I have, let's call this identity matrix. Actually, let's change our identity matrix. It won't be an identity matrix anymore, but let's just change our numbers up so we can better identify them. So let's do the first row, second column. So the result should be 4. So I, open bracket, first row, comma, second column is equal to 4. For the next topic, I want to start a new page so we didn't have x pre-assigned, and that is our differentiation and integration. We have our shortcuts for derivatives and integrals in our functions toolbox. But before we do that, let's assign y to be equal to 10x squared, so 10x raised to the second power. Now we don't know x. If I type x equals, it's actually asking me to assign a value to x, but I don't have a value for it. Not yet anyway, so we can just leave it as it is. So for our first derivative, we'll click on our toolbox. So we'll have the derivative of y with respect to x. And if we hit equal, it's going to be undefined because x isn't defined. What SMath is able to do, it's able to evaluate this symbolically, however. So let's get rid of this equal sign, backspacing a few times. And I'm going to press Control period, and we can see that symbolically the derivative of 10x squared is 20x. We can also do higher order derivatives. So we'll come back to our toolbox, and y, that's what we're going to take the derivative of, and we're going to take it with respect to x. But if we want to do the second derivative, or any higher order derivative, I'm going to press the comma, and notice it allows me to put something for a higher order, so I can do 2, or I can do 5, or whatever it might be. Let's do 2. If I hit equal, it actually gives me 20. Now I didn't determine this symbolically. This is the actual value, and the reason for that is because the derivative, or the second derivative of 10x squared, is indeed 20. It is not dependent upon x. Now let's say I were to put a 2 for x. I get zeros. You might wonder why. The reason is because y is now a constant. Y is equal to 40. And so the derivative of 40 is 0. And the second derivative of 40 is also 0. Now the way to get around this is to take the derivative not of y, but of 10x squared. So I'm going to select that portion, Control C, and then I'm going to paste it where y is, Control V. Now we see the derivative of y with respect to x at 2 is 40. We can do the same thing here, and that should bring us back to 20, which we found earlier. If we were to change 2 to 5, our first derivative changes, and our second derivative is constant. Knowing this, let's see if we can determine the radius of curvature of an equation of 1 over 20x squared at x is equal to 10 meters. Here's our equation, and we see that we have the first derivative in the numerator and the second derivative in the denominator. And I want to do this for two reasons. One is because it gives us an example of doing derivatives, but also I haven't really discussed parentheses in our equations earlier, so this makes a good example to use our parentheses. So r, we're going to assign that to b. I'm going to open my parentheses, 1 plus, I'm going to open my parentheses again, and we're going to have the first derivative, and so I'm going to take the first derivative with respect to x, and we're going to use our equation that we have here, our 1 over 20 times x squared. I'm going to copy that over. Now this derivative is squared, and so I'm going to need to use my arrow keys to move around to get so I'm outside the parentheses, and here we are. Now I'm going to raise that to the second power. Now I need to have my parentheses that we see here to raise to the 3/2 power, I can also use my space bar. Now I'm going to raise this to the 3/2 power. Now this will all be over the second derivative. So I'm going to use my space bar again to select all of that. Then the slash. Then I'm going to have my second derivative. So I'm going to use my derivative function. And I'm going to have this copied to Control C, Control V. And that's with respect to x. And now I'm going to press the comma to get to my second derivative. Now our equation has absolute values, and it has it over the entire equation, which is fine. We actually only need it over the denominator because the numerator is always positive. But regardless of which way you do it, you want to make sure when you use the absolute value that you get it from the arithmetic box and not from the matrices determinant. And so I can select that and then press the absolute value button, and we can see that the absolute values are there. Let me zoom in just so that we can see that. And now I can press R is equal to. It gives me a problem. It says my units don't match. We can run into problems using units in our derivatives. So I'm going to remove our unit, selecting it and backspacing a few times. And now we see that we have a radius of 28.3. Knowing that x was originally in meters, so is r. Let's quickly look at integration. To do an integral, we could only do definite integrals. So we are going to use the button, definite integral. Let's have 3z squared dz, and let's go between 0 and 2. Then I can hit equal, and that gives us 8. We can't do integrals symbolically in SMath. Our next section is user-defined units and change of temperature. Let's say we had a pressure, P, and let's assign this to be 15 psi. I can call out that pressure. I'll say P equals, and we can see what it is in pascals, and we even can see kilopascals, or even inches of mercury. But what about inches of water, or inches of H2O? That isn't available to us, and we can see when we try to put something like that in, it basically just cancels that unit out, inches of H2O divided by inches of H2O, and then it has kilograms per meter per second squared. So to make our own unit of inches of water, I'm going to press the single quote button. That's going to activate my units. I'll type inches, or INH2O, and you can make it whatever you'd like it to be. We'll assign it to a unit of atmospheres, where 1 inch of water is 0.002458, and then I'll press the single quote atmospheres. Now if I type pressure again, or P, and have that equal, let's go ahead and change this to inch H2O, and that is our customized unit. We can also get into a problem with SMath when it comes to changes of temperature. Let's say we had a temperature, T, and let's make that to be 100. I'll press a single quote, and we can press degrees C, and double click it. And I can call out T again, press T then equal. We can see what it is in Kelvin, T equal, and we can change this to press a single quote to degrees Fahrenheit. Here it is. And that all works just fine. However, let's try something. So let's say that T sub 1, I'll press the T period 1. Let's make that to be 100 degrees F. So let's make T2. Let's assign that to be 0 degrees F. Now let's do T1 minus T2. We get Kelvin, that's the default unit, so let's just change it to Fahrenheit, or degrees Fahrenheit. We have minus 360 degrees. Well, why is that? Well, let's do this. Let's go T1, T2. We'll leave the default units of Kelvin. And we can see that the difference is about 55, 56 degrees. Let's put this back into Kelvin. So here's what happens. It takes T1, converts it to Kelvin, takes T2, converts it to Kelvin. Then the difference between those two is 56.6 Kelvin. And let's just call delta T equal 55.6 Kelvin. If I make that equal into Fahrenheit, or degrees Fahrenheit, we'll get that 360 again, or negative 360. So what do? We need to use a delta C or a delta F when we're using change of temperature. So here we have temperature 1. I'll add the capital D, control G. We can see that we have a change of temperature. We can see that we have it for Celsius, Fahrenheit, and this unfamiliar temperature range. Do the same thing here. capital D, control G. The change in temperature has to be in delta F. So capital D, control G, and here it is right here. So 100 Fahrenheit minus 0 degrees Fahrenheit is 100 degrees Fahrenheit. Let's get rid of this. We don't need it anymore. Let's see, we needed the change of temperature in an equation such as thermal strain. And thermal strain is just epsilon, so E control G, and that's equal to alpha, thermal coefficient of expansion, our coefficient of thermal expansion, times T2 minus T1. We haven't defined alpha yet, so let's define alpha up here. And for aluminum, that would be 12.8 times 10 raised to the 6th power. No, that would be minus 6, I should say. And then the units, it's 1 over degree F. So 1/degree F. Now, if I were just to put the degree F in there, we may get a problem, seeing our units don't match. So let's make sure that this is delta. And here is our thermal strain. So we can see when the original temperature is 100 degrees and then changes to 0 degree F. That results in a negative thermal strain. Our last topic is plotting. And we can either get to plotting by going to Insert and then Plot. And we're just going to look at 2D plot. And we can see there's an asterisk there. And so we can click that and that gives us a plot. I can select it and then delete it. And the other way to do it is just clicking anywhere on your sheet, and Shift 2 or the asterisk gives us a plot. To create our function, all we need to do is just create a function of x. So there's sine of x. We just type x. There it is right there. One thing to note that notice that x has been predefined, but that doesn't affect our plot. So in our equation or in our function, any predefined value of x is ignored. However, if I were to have y is equal to 2, and then come into my function down here and type y, we can see that it is 2, or let's put 4 there. Should go right on that line, as it shows there. We can select the graph and then right-click for some more options. One is that we can turn our grid on and off. I think it looks a little bit better with the grid on, as well as our axes. And then we could also include a description. And that is it. Thank you for watching.